Hello everyone, I'm Christophe Verbist. I work at the University of Antwerp, PhD student, together with Stefano, which is a master student, and my promoter, Michele Giuliano. Our research is focused on the dynamical properties of cortical neurons in silico. And I'm going to start with the basic property of a neuron and of an action potential that is very crucial to our work. And it's that the action potential that is generated at the soma has a much sharper spike, has a much sharper onset, than is explained by isopotential membrane theory. So we need new theories for that. And there were several proposed theories, but the one that seems the most likely now is critical resistance. This was a theory proposed by Brett, I think in 2012-13 maybe. And this basically states that there is an impedance match between soma and axon. Now, I'm not going to go into the details of this theory because it's a very mathematical theory, and I don't want half of the auditorium to fall asleep, so I will just go on with some of the consequences that are important for our work. The major consequence, which was to me very counterintuitive, is the following. If you look at the top picture, what we see here in dashed lines is the voltage trace of the axon, and in full lines and solid lines, the voltage trace of the soma. If we move the axon initial segment, which is where the action potential is generated in the axon, away from the soma, then we see that the time difference between the spikes increases. So the further we move the initial segment away, the more easily it is excitable, or the more excitable it is a better phrase. Which is very counterintuitive, because if you move something further away, it becomes more excitable. No, it should be the same, or it should be even less excitable, because the current needs to travel more distance. But apparently, the model confirms this is not the case. If you look at another consequence of this theory, we can see this in the bottom figure. If you look at the change of voltage in the soma, with respect to its own voltage, we see that for the normal case, which is the purple line, the soma has this famous kink, and it's biphasic. So the action potential rises very fast first and then slower towards the end. Now we can remove this kink, as we see in the red curve, if we move the initial segment and the soma very close together. And this basically just confirms what we see in the top figure. Both soma and axon become less excitable, because the generation of an action potential goes slower. So now our main question, the research question, is this. Do these properties have an influence on the cutoff frequency? Now you might ask yourself, the cutoff frequency, that's the first you said about it, yes, and I will explain it in a moment, what I mean by it. I'm going to spoil it for you. The answer is yes, it does matter. So what are the models we are looking at? We are looking at a two-compartmental model, basically just a soma and an axon. In both of them, we have normal Hodgkin and Huxley equations, which some people will now hate me for saying that we don't use integrated fire, but we actually need Hodgkin and Huxley here because we are interested in this. If I go back, we are interested in this very first part of the action potential, which is the one thing the integrated fire neuron doesn't have. So that's why we need it. And we connect them by an axial resistance. And this axial resistance just acts as the distance between soma and axon. If we increase this axial resistance, the distance will increase. The virtual distance, because there is no real distance in this system, of course, will increase as well. Now we inject a current into the soma. And this current has three parts. The first part is an Ernst-Uhlebeck process, which is just a fancy name for a random number. The two other parts, the last part is an offset, and the offset basically just guarantees that the neuron is firing at a certain frequency. It's not that important. But the most important part is the sign. And this sign we will change in frequency. And now I will say that if I inject this sine current into my soma or my neuron will follow this sine current. And what do I mean by follow this sine current? I mean that when the input sign is at its maximum, the neuron will fire more, just because it has more current. When it's at its minimum, it will fire less. And so we can I deleted the slides because I thought I wouldn't have enough time, so I will use my awful drawing skills. I apologize already. So we can basically create an histogram of spike times. So if this is my input sign, and then my neuron will spike way more here, and it will go slower here. And so you can already see that if we bind these times together, we can create some sort of histogram. And by creating this histogram, we can fit a new sign to this, and this is then the input sign of our neuron, the output sign of our neuron, I'm sorry. And we do this for a very long time, so we just cut every period of the sign, and we put them on top of each other, and then we fill this histogram, which will become big enough to actually fit a sign to. Now this method is actually inferior, so I just wasted 2 minutes of your time, I'm sorry. The best, or a better way to do it is circular statistics. In the lab I have another name for it, I call it circular black magic. But there is actually no magic involved, it's just some basic math. But it does actually the same. And what we are interested in is this amplitude of the sign. If we increase the input sign frequency, this amplitude will die out. There is a frequency at which the neuron will no longer follow it. And the neuron will just see a DC current. And so that is the cutoff frequency. Now if you go to some of the results, the most important results we see in the top left figure, we see the FI curve of different models with different actual resistances. So, I repeat, different distances between soma and axon. We see, as we expect, if we increase the actual resistance, so if we increase the distance, the system becomes more excitable, so the slope of this FI curve becomes steeper, which is already what we expected. If we now look at this magnitude, this famous magnitude that I so beautifully drew here, and we see that after a while, after a certain input frequency, this is the frequency of the input sign, so not of the firing neuron, we see that that this amplitude goes down to almost zero. It's a log-log scale, so don't be fooled. And if we try to fit this with a border diagram, which if you're an engineer you probably know, and if you're a physicist, if you know it, then good. I am a physicist, I didn't know it, so. And we can see here, these are the poles of these border functions, and these poles are basically the cutoff frequencies. And so we see that if we increase the actual resistance, we actually increase this cutoff frequency as well. And so to conclude, the first point I didn't talk about, but it's logical and it's not even worth mentioning actually. But if you increase the standard deviation of the noise of this Ernst-Uhlenbeck process, you actually lose the relationship between the input frequency and this magnitude. You no longer have a cutoff frequency, you more or less have a noisy flat line, which is normal. I mean, if your noise is so big that your input just doesn't have a sign anymore, then your neuron won't have a sign either. And the last thing we just talked about, so I don't have to repeat that. I want to thank you for your attention, and if you have any questions, I'll be happy to answer them now or at the poster, I think 27? I have no idea actually, sorry.